All right, cool. All right. So let's now do an example with a slant asymptote. Who has an example ready? If not, I'm going to make something up. Does anyone have an example? Yeah.
What about x cubed over x subtract 1 squared?
X cubed over x minus 1 all squared?
Yep.
Yeah, totally, we can do that one. Okay, let's do it. So, f of x is this. I'm just going to partition the board here, okay? All right. F of x is x cubed over x minus 1 squared graph, okay? Okay, so there's our equation, and we repeat the steps, okay? It's a curve sketching question, so let's repeat the steps quickly this time. I'm not going to explain what the steps are, they're right there. Okay, someone shouted out.
All of the real numbers except 1.
Very good. I'm going to write it as arm minus set 1. Or I'm going to write it as negative infinity to 1 union 1 to infinity. Okay? Or I'm going to write it as x in R such that x not equal to 1. These are all equivalent. Make sure you understand how to write the domain, because you lose a mark if you don't have the right form. Okay? Step 2. X and y intercepts. X int. What's the x int? Come on, quick.
X equals 0.
Very good. Set it to 0. Top must be 0. X is 0. Okay? Y int. This is the easy one. You sub in x equals 0. What do you get?
0.
0. Cool. So, these two together tell us that f passes through the origin. Okay? F passes through origin. Okay? Cool. That's useful information right there. 3. Okay? 3 is asymptotes. So, vertical asymptotes.
X equals 1.
Very good. X equal 1. You look for the problem point, in this case division by 0. Okay? Now, the part that we actually want to do. The slanted asymptotes, or the oblique asymptotes they're sometimes called. How do we find the slanted asymptote?
Divide the function itself.
Yes. You divide this polynomial by that polynomial. Now, you can do it with long division, or you can do it by messing around with the top and messing around with the bottom and trying to get them to divide out. Okay? I know, that seems like a lot of messing around, but sometimes the second way is easier than the first way, especially if you forgot how to divide polynomials. Okay? X cubed over x minus 1 all squared, right? Right? That's just this equation. Okay? And now what exactly do I mean by messing around? We're going to add and subtract stuff to the top. Okay? The stuff we're going to add and subtract is going to look like the bottom. So here's what we're going to do. This is x cubed minus 2x squared plus x plus 2x squared minus x over x squared minus 2x plus 1. Okay? And now, what does that equal to? We're going to split the division like this. This part, and then add that part on. Okay? So here we're just going to get an x. Okay? And then we're going to get plus 2x squared minus x over x squared minus 2x plus 1. And then we repeat that step over here. So subtract away to get a multiple of 2 here. So subtract 3x's, add 3x's, and so on. Okay, you can do it that way. In this case, that method sucks because it's messy and it doesn't help you. It's slow. Okay? But in some particular cases, it's very easy. Okay? So just so you know, you can add and subtract the same thing from the top and not change the thing and then nicely divide it up. Okay? In this case, let's just actually divide the polynomials, because this is just too messy and you could make a mistake. All right, so to find this, okay, you're going to divide, okay, the polynomials. Okay? So how do we divide polynomials? set up our quotient, okay? And then what do? We have this here, and then here's where we put our x cubed, right? Yeah? Now, if it helps you, we can do this. Okay? Plus 0. Okay? And now we think, what do we need to put up here such that when we multiply it by this, it's going to cancel out the first term?
X.
X, exactly. And let's just line it up with the x over here. We multiply x by this, we get x cubed minus 2x squared plus x, and then we subtract them out. So the x cubed should cancel out, so you should get a 0 here, and the degree is reduced by 1. Now you do 0x squared minus 2x squared, which is plus 2x squared, minus x, okay? Bring down the next term, plus 0, okay? You can see the benefit of putting the zeros in, all right? Now, what do we have to put next?
1.
2, yeah? Plus 2. 2 times that, 2x squared minus 4x plus 2. Subtract, 0 plus 3x minus 2. And lastly, what must we put? Nothing. We're done. Okay? How do I know we're done? There's no way to cancel that. Okay? We have an x squared there. So this is the remainder term, and the result of our division is this. That x cubed over x squared minus 2x plus 1 is equal to x plus 2 plus the remainder term. So 3x minus 2 divided by the bottom. There we go. All right? Now, where is the equation of the asymptote, the slanted asymptote? Yes, very good. This is the oblique asymptote. Make sure you understand why this works. Why does it work? When we're looking at a slanted asymptote, we want to see what happens to f as x gets large, right? It's the same process as we're looking for horizontal asymptotes, except we're not just straight up taking the limit as x goes to infinity, because in this case we'd get infinity, or negative infinity, okay? Anytime you have a slanted asymptote. But you're looking at the end behavior, okay? If we take this thing now and look at what happens when x goes to infinity, this part goes to 0 because of the degree. The degree is larger in the bottom than at the top. That part goes to 0 as x goes to infinity. And what does the function behave like? What does it look like? It looks roughly like that line, x plus 2. This function, for large x's, is roughly x plus 2, plus something which gets vanishingly small, okay? That's how you know that the function roughly behaves like that line, which means the function approaches that line in the limit. It's a slanted asymptote, okay? So always think. Don't just memorize steps, okay? Because you'll forget them on the exam. You try to memorize things, it's easy to forget. I'm going to plug my phone back in. There we go. Okay. So that's how you find that. There is another way to find the slanted asymptote. Okay? You can multiply, or rather you can divide by x and take the limit as x goes to infinity. Okay? So the second method, if you don't like division, second method, you want to find the equation y equals mx plus b. Okay? In order to find m, what do? You divide by x and take the limit. M is the limit as x goes to infinity, f of x over x. You can see why that works, right? Because if f is roughly a line, and it has some slope, f is roughly equal to mx plus b for large x's, you divide by x, f of x over x is roughly m plus b over x. The b over x term will go to 0, and this thing will approach m. Okay? So another way, if you prefer limits to division, is you can evaluate that limit, and that gives you m. Okay? The slope. How do you get b? In a similar way. Now that you have m, you can take your function f, subtract away mx, and take the limit as x goes to infinity. Limit x goes to infinity, f of x minus mx. Okay? We're subtracting away the line component, and we're getting the b value. Okay? That's the slope of the line. we're getting the b value of this. There we go. So there's our two formulas. And you can see why they work if you look at this example. You divide through by x cubed, that reduces to x squared. And you can see that, oh yeah, x squared over x squared minus this stuff does actually tend to 1. So the slope formula works. And then you can see that, well, if you subtract away x here, okay, after, so f of x minus mx, you subtract away x, take the limit as x goes to infinity. This part is going to 0, like I already explained, and the limit's going to be 2, the b value. Okay. Yeah, you have a question?
Yeah. What if x approaches negative infinity? There's sometimes you have a right slant asymptote and a left slant asymptote.
Yeah, you'd need to just check for both of them.
Then how do you know when you have only one and when you have two?
You don't. You have to just check. Okay? You'll know because, first of all, that situation that you're describing can't happen with polynomials. Okay? With polynomials, when you divide, you always just get a single line. Okay? So that situation that you're talking about can happen with other functions, but not with polynomials. Here's an example of where it can happen. Oh crap, there's no spot. Okay, here. Yeah, okay. Here's an example of what you were talking about. The square root of x squared plus 9. Okay? What does it look like? We have asymptotes here and here. Okay? There we go. And the function looks like that. Okay? It looks like a U shape and it approaches the lines x and negative x. All right? How do I know that, by the way? Root of x squared plus 9, as x gets large, the 9 doesn't make any difference. So this is roughly root x squared, which is absolute value of x. So the asymptote looks like an absolute value. Okay? How did I know the function is above it? Because I know that at 0 it equals 3. So there's the function. Yeah?
How would you check for that? Which are not polynomials?
Yeah, like I just explained, just think through it.
Yep.
Take the limit to figure out what happens when you have a large x value, okay? And you'll see that the 9 doesn't make any difference. You get root x squared, which is abs x roughly. Or you use this more general thing that I told you, okay? You divide only when you have polynomials. If you don't have polynomials, you use the second method, okay? So this is for no polynomial. Okay? It also works for polynomials, but it also works for any functions at all. Divided by x, you divide that by x, and then you take limits. In this case, there are two cases, because root x squared could be plus or minus. Or rather, sorry, this is always plus. But when you divide by x, the x could be plus or minus, depending on whether you go to infinity or negative infinity. So you'll see that the limit is going to be either plus or minus 1. And then to find the b value, you take this thing, you subtract x, and then you find the limit there, okay? You subtract away x like this and take the limit as x goes to infinity, or you subtract away negative x and take the limit as x goes to negative infinity, okay? And how do you evaluate such a limit? You rationalize it, okay? So multiply, divide by the conjugate, okay? It's good coffee. By the way, guys, if you want to up your caffeine intake, I always now ask for a double shot of espresso in whatever coffee I get. So that was a black iced coffee with a double shot of espresso.
You will not sleep.
How do you go to sleep?
Ah, that's fine. Yeah, so if you need some extra energy for the exam, that's what you do. All right?
Good you.
Yeah. Okay.
This could be a movie.
Yeah, so let's finish this question because we never finished it. Okay, we're gonna erase this. We'll finish this question and then maybe we'll take a short break if you guys want. I don't need a break, but maybe some of you do. Okay, so the slanted asymptote is here, x plus 2. Okay, what's the next step? After asymptotes, you do what? You take derivatives. Okay, so step 5. Okay, let's take the derivative. Okay, so we have x cubed over x minus 1 all squared. That means quotient rule. 2, 3x squared, derivative of the top, times the bottom, minus the bottom derivative, times the top, over the bottom squared, which is to the 4th. Okay? Now, it's not as hard as it looks. Here's a hint. Don't expand out the top yet. Okay? anytime you use quotient rule and you have like a squared bottom, okay, there's going to be a copy that'll cancel out. Okay, you're not going to get fourth power at the bottom, you're going to get cubed. Okay, so cancel, cancel, cancel. And then we'll expand after that. So 3x squared, x minus 1, minus 2x cubed over x minus 1 cubed. And that looks a lot better because at the top we have a cubic. At the bottom we also have a cubic, but the thing is the bottom is nicely contained. It's just x minus 1 cubed. Okay? It's not gonna make anything difficult for us. It's the top that we have to worry about when we then set to 0 and stuff, right? So let's just expand that out. We get 3x cubed minus 2x cubed, which is x cubed, minus 3x squared, okay? Over x minus 1 cubed, and this nicely simplifies. It's just x squared, x minus 3, over x minus 1 cubed. Okay, critical points. What are the critical points?
X equals 0, x equals 0.
You set the thing equal to 0 to find the critical points for the CPs, okay? And when you set to 0, the bottom doesn't matter. You just set the top to 0, right? Something over something 0 and the top is 0, yeah? Okay, so you set that to 0, we get x equals 0 or x equals 3. Okay? There we go, so we get 2 critical points there. Now let's take a look at the sign. So this was 5.1. This is step 5.2, okay? Signs of derivative. So in this case, we draw our table here, okay? And we label 0 and 3, okay? We also want to label the asymptote, okay? Keep that in mind. Some students forget that. The sign of the derivative could change at the asymptote, okay? So label the asymptote as well. Asymptote's at 1. So I'm going to put 1 there, and I'm going to put 3 out here, okay? And now we're just going to check the sign. When x is negative, so this column here will be labeled, this will be sign of f prime, okay? So sub in a number, okay, to the left of 0. Sub in negative something. What is the sign of the function? Where's the function? There it is. If you put in a negative, what do you get? Positive or negative?
Wait, aren't we looking at the derivative?
So, oh, that's right. Okay, never mind. Sorry about that. Yeah, we are looking at this. If we sub in, so that's why everyone was so quiet. So if we sub in something negative, what do we get?
Negative.
Negative, okay? Notice that this thing, okay, that doesn't matter. That's always positive. So let's just ignore that part. Let's focus only on these two. We sub in something negative, we have negative, negative, negative over negative is positive. Okay. If we sub in something between 0 and 1, in this case we might actually have to sub it in. Let's put in a half. Okay, we already said this part doesn't matter. Here we get a half minus 3, a half minus 1. They're both negative, so it's positive again. Okay? Between 1 and 3, let's plug in 2. What do we get? That we ignore. Negative 1 over 1 cubed. Negative over positive. Negative. Something bigger than 3, let's say 4, positive, positive, positive. Okay, so the sign of f prime looks like this, and then we can add in another row to the table, but only if you want to. F is increasing, F is increasing, F is decreasing, F is increasing, okay? And then we're gonna figure out how to draw that, okay? So there's some hints. We're just about ready to draw right now. Do you guys want to find the second derivative and stuff?
No.
Yeah, screw that. All right, let's draw the thing. And if we're wrong, by the way, we'll find that out because we're going to Desmos this right after we draw it, okay? So if something comes up on Desmos, which is unexpected, then we're going to go back and do the second derivative, okay? So, graph, all right. All right, we need a lot of space this time. We have an asymptoted 1. Okay, there's x equals 1. We have something at 3, right? 3 is a critical point. 0 is a critical point. Okay, the function passes through the origin. Okay? So there's a point over here. Okay. The slanted asymptote, let's get that. X plus 2, right? So let's say this is 2, okay? So the slanted asymptote looks like this, all right? There's our slanted asymptote, okay? So vertical asymptote, slanted asymptote. And now we want to draw this thing in such a way that we get all of this information in, all right? So at the point, so to the left of 1, the function is always increasing, okay? Function is always increasing, yeah, positive, positive. Function is always increasing, and we want it to approach these asymptotes. Did we mess up?
No, it's right.
It's right?
You need a second derivative.
Wait a minute. If it passes through the origin, how can it always increase to the left of 1?
I think it passes the.
What the? Wait. I know how to solve the problem. Okay. Yeah, so someone's saying
See,
that
one is it's like a maximum.
I guess we will say that.
That was a good one.
Wait a minute.
What? Reduce this. No, yeah, it's an inflection point.
Oh, this graph is crazy. Okay, yeah. So
Let's take the second derivative.
yeah, it's the second. Yeah. Okay, so at this point, yeah, you go back and you do the second derivative. So all the information is right, okay, but the function does something that I didn't expect, which is to cross the slanted asymptote in the middle, okay, which is allowed. You can cross a horizontal asymptote or a slanted asymptote, right? Many times even. Yeah, right? The function sine x over x has a horizontal asymptote at 0, yet it crosses it infinitely many times. So you can't. The function x plus sine x over x has a slanted asymptote. However, again, it crosses, or x squared plus sine x over x. However, it crosses it infinitely many times. So you can cross a slanted asymptote or a horizontal asymptote many times. Okay? In this case, we do cross it. So the function approaches the asymptote down here, okay? And then it does something real weird. It just goes like that. It has like an inflection point, something at 0, and then it goes up, and it approaches that vertical asymptote.
Because why not?
Yeah, because why not, right? See, if we took the second derivative, it would get us that inflection point. But we were too lazy to do that, okay? But what is the lesson from this?
Always take the second derivative.
Okay, sure. That's one lesson. But another and more important lesson is that, because you don't need to take the second derivative, I was thrown off by the fact that the function would have to cross the slanted asymptote. I thought if it's increasing, increasing, I was about to draw this, right? Which would have been fine, but then I remembered that it has to pass through the origin, and then for a second I was like, did we make a mistake? It's possible that we could have made a mistake, but not so fast. Okay, keep in mind that we could actually cross a slanted asymptote in the middle. Okay? I just forgot about that for a second. But if I kept that in mind, I could get away with not having to do the second derivative, which was the goal here, right? So anyway, that's what the function does. To the right, okay, we have better behavior, because to the right of 1, we know the thing is decreasing, okay? And then after 3, it's increasing. So 3 is a minimum, okay? So what I would assume the function does is this. Now again, in order to confirm all of this, we'd have to do the rest of the steps. So I said there were 9 steps. What comes after this? Okay, so step 6 would be to actually find the points, okay? Find extrema. Okay? Now, How do we find the extrema? What I'm talking about is we actually plug in the point 3 and see what is the height of the function there. We want to get the actual point because that'll tell us where the min here is, okay? So I would assume that this point here, the way I drew this, you know, this thing is at 3 comma something. I want to find the something, okay? That's step 6. To get the something, you just do f of 3. And in this case, it'd be 3 cubed, so 27 over 2 squared. So 27 over 4 is what? Like 6.75. So this is at height 6.75, okay? So it's up here, so we know we got this right, okay? So that would be step 6. Step 7 would be to actually find the second derivative, okay? Step 7 would be to find f double prime of x. I'm just going to do it real quick because I just want to see if the 0 actually comes out. Okay, so let's take the derivative here. F double prime of x is derivative at the top, 3x squared minus 6x. I'm using this one, okay? Times x minus 1 cubed minus 3x minus 1 squared times x cubed minus 3x squared. Let's just do this real quick, okay? To the power 6, cancel, cancel, cancel. We get 3x squared minus 6x times x minus 1 to the 1, yeah, minus 3 x cubed minus 3x squared over x minus 1 to the 4. Okay, can we do it in one more line? 3x cubed minus 3x cubed. Ah, cancels. Okay, great. 6x times that, so negative 6x squared minus 3x squared, so that's negative 9x squared plus 6x plus 9x squared over x minus 1 to the 4. The 9x squareds cancel out. Look at this, it's so simple. It's only 6x over x minus 1 to the 4. Okay, great. It all just magically works out with these textbook questions. Now you can see that there's only one inflection point and it's 0, which is what we already knew. So this is the inflection point. That's step 7. That's step 7.1, okay? Is the critical point of the derivative, okay? Step 7.2 is concavity, which means you to the left is 0, to the right is 0, to the right of 1, okay? And you see what the concavity is, the sign of f double prime, okay? In this case, you get negative second derivative, positive second derivative, positive second derivative, okay? That's step 7.2. Step 8 is the actual points of inflection. Remember that the second derivative could be 0, and you will not have a point of inflection, possibly. Yeah? You guys know that? Okay. You've got to check if the concavity actually changes sign. An example of a function which has a 0 second derivative but no inflection point is x to the 4, right? It has a second derivative 0 at 0, but it's a min, okay? It's not an inflection point because the second derivative doesn't change sign, okay? So step 8 would be draw your table, or step 8 would be rather identify the inflection points, okay? From the table you drew and from the critical points, figure out which of those are inflection points and which of those are possibly something else. And then step 9 is to draw the graph, okay? So we have actually done all the steps here. Of course, steps 7 and 8, we just sort of hand wave, because we know the answer already, right? But yes, this is how the graph looks like, and these would be all the steps that you'd be required to do for full marks. Yes?
Okay, question about the first derivative on the when it's less than 0.
Yeah?
We did the sine part, right? We got it's increasing full time, right? But clearly, if you look at the graph, first derivative is obviously decreasing as it goes to 0. Like, look at the graph there, right?
It's increasing as we go to 0.
No, like the first derivative, not the function.
The first derivative is decreasing, yeah. Is decreasing. But the first derivative is decreasing means the sign of the second derivative is negative. the second derivative is indeed negative, right? It's 6x over x minus 1. It's negative to the left of 0 and positive to the right of 0, right? So it's negative here and positive here and here, right? As expected from the graph. Yeah, so that part's actually okay. By the way, when you're asking about increasing, decreasing, remember to always go left to right, okay? Some people forget that. They think, oh, but if I go down here, I'm sliding down, so it's decreasing. No, you go left to right, okay? The function is increasing in the back.
Also, we have to find the point where the graph intersects the slant asymptotes.
If you want to. You won't lose marks for it. I don't know the answer to that question. Yeah. I mean, you can find it. Just set x plus 2 equal to, you know, this, and then solve. But the thing is, you'll get a cube equation. It's going to be hard to find that point. You know, in this case, it could be done, but it might be hard. Okay? Yeah, I don't know. In this case, you would just raise your hand and ask that question. Yeah. Yes?
How do you know the graph doesn't intersect the slant asymptote again on the right?
Yeah, like y doesn't go cross the slant asymptote and then passes and moves upward from up to 3.
Yeah, good question. How do I know that it does this rather than down?
And
Because
then-
if it went down, okay,
and
and
it doesn't cross the slant asymptote, it just approaches it.
yeah. See, how do I know that? I think about what criteria we have. If you look at the second derivative, it's always positive to the right of 0, which means the function has to have a U shape here, okay? We can't cross, I get what you're saying. What you're saying is, we could cross the slant asymptote, and this is a really good question. We could cross the slant asymptote and then come back up. But here's the thing. If we do that, yeah, we are decreasing and then increasing. But if you really think about it, in order to then approach the slanted asymptote, we would need an inflection point right there, okay? That forces an inflection point to be here. If we go down below the asymptote, we want to end up approaching the asymptote. We want to end up getting closer and closer to it. If there's no point like this of inflection, we would end up crossing it right across eventually like this, okay? And then going off somewhere, not approaching. In order to approach, we would need, you know, this kind of behavior, where we start getting closer and closer like this. And that would force an inflection point there. Okay? Good question though, yeah. Yeah.
And what it y, like this?
I think it will
almost
have
works
more
from
inflection point.
Yeah, you'd have more, yeah, just, so this is a particularly like nasty example because you see a question like this, you might see, you know, you might see a cube at the top, but the bottom would be, you know, also a cube, or, well, no, actually you wouldn't even have that. You might have a quadratic over a quadratic, or you might have like x over, you know, 2x squared minus 3x plus 5, for example. Okay? So expect something that factors in the bottom, and expect not too much, you know, craziness. Okay? And all functions which look like quadratic over quadratic or linear over quadratic, usually you don't even have to find the second derivative. You can just get exactly what the function looks like from steps 1 through 5, and it would look in the way that you would expect. There wouldn't be much crazy stuff happening. If you have a cubic degree, there might be some crazy stuff happening, like the crossing of the asymptote, but not too crazy. Okay? All right, do we need a break?
No.
Now we're good.
Okay, cool. All right, so any other questions about this question? Because it's going to get wiped. Do we need a break? Oh, okay, so if there are no more questions, I'm going to wipe this away, and someone is welcome to ask another question. Yeah.
Do you have a good example of integrals?
Integrals.
Yes.
It depends on what you did in the class.
The indefinite integral.
All right, let's go over the most important ones.
Like the basic.
Yeah, the basic ones. Okay, let's just go over some let's just go over some basic indefinite integrals. Okay, so basic indefinite integrals. What are the most important integrals that you got to know? Here's the most important one, okay? Here's the most important one. We're all going to yell it out, okay? What's the antiderivative? By the way, indefinite integral and antiderivative are the same thing, okay? Antiderivative. What we're doing, antiderivative, okay. What we're doing is we're looking for a function whose derivative is, you know, the function that we're giving here, okay? So if I ask you about the indefinite integral or the antiderivative of a function, you want to find another function that differentiates to it, okay? So let's just make sure we're all clear about the rules here, okay? So, I'm going to get rid of that one. Let's do this in a table. Function, okay, and the antiderivative. There we go, okay. All right. First example, we're all going to yell it out, okay? What is the antiderivative? This is going to be hard, okay? So prepare yourselves. X.
X squared over 2.
Very good. Okay. X squared over 2. How do we know?
Differentiate on the antiderivative.
Yeah, we take the derivative and we see that, oh yeah, it's x. Cool. All right. That's the first one that you ever learned, okay? What about a power, x to the n?
X power of n plus 1 is like
Okay. Cool. So we do the opposite of the power rule. We add 1 to the exponent and divide by the exponent plus 1, rather than drop the exponent and subtract 1. Okay? And how do you test it? Differentiate and check. All right? That's always how you check. Okay? Just take the derivative. Now, there is a small problem here. So when x is -1, that formula doesn't work because we end up dividing by 0. Okay? So this only works if n is not equal to -1. It works for everything else though. Like it works for even fractional things. Like it works for exponent 1/2 or like exponent pi or whatever, you know? Not necessarily just integers. But it does not work at -1. So that leaves the question of what is the antiderivative of x to the -1 or 1 over x?
the ln of x.
Yeah, the log of x. Okay? Or do you guys use like ln? Yeah. Okay. That's only in first year. Later on, people just use log to denote the log base e. Yeah?
But you also have to include the absolute.
Oh yeah. Good point. Okay. There we go. It depends on where you want the formula to be valid. So for instance, if you only want it to be valid for the positive x's, then ln of x is fine. If you want it to be valid everywhere but at 0, then ln of abs x is the way to go. But yeah, technically you are correct because we want to make the formulas as general as possible. Okay? So, you know, put the abs in here. But I mean, again, it wouldn't be wrong not to put it in. It's just you might end up losing a mark or something if you're expected to find the most general formula. But you could write ln of x and then specify for x greater than 0. Okay? In this case, you'd have, you know, this is true, you know, for all x's in R. For all x's in R. This one is true for all x's in R except at 0. Okay? And ln of x, you know, is true for all x's, you know, in R that are strictly greater than 0. So the formula ln of x is still okay. It's just that the domain here is different. Okay? All right. Some other very important functions. We just took care of power functions. What about trig? Sine. What's the antiderivative? Quickly.
Negative cosine.
Negative cosine x. All right? Right? Just take the derivative. Negative sine. Yeah. Cool. Okay. Cosine. Yeah. Antiderivative is sine x. All right. Tan x. Ah, gotcha. What's the antiderivative of tan? Here's how to think about it. tan x is sine over cosine. Yeah? Tan x. Okay? Let's think this through over here on the side. Let me just erase this. Okay? So, tan x is sine x over cos x. Okay? And this is what I'm going to notice. That sine x is almost the derivative of cos x. Okay? It's negative, the derivative. So, tan x looks like this. Yeah. It looks like that. For f of x is equal to cos x. Can you guys see that? The tan x is cosine x, 1 over, okay? Above it, we have negative the derivative of cos, okay? So you can write it as this, negative cos of x prime over cos of x. Now, why does this help? We know of a function whose derivative will look like that. If we take the derivative of ln of f of x, the derivative of ln is 1 over. So this is going to be 1 over f of x, but we need to multiply by f prime by the chain rule. Okay? Chain. So, 1 over the function times the derivative. If we see something that looks like the quotient of the derivative over the function, we know that the antiderivative of that thing is ln of the bottom function. So, what is the antiderivative of tan?
Negative ln cosine x.
Very good. Tan x, negative ln cos x. And you can check it. Take the derivative of ln cos, you get 1 over cos times the derivative of cos, which is negative sine. Negative sine over cos, negative goes away. Sine over cos, which is tan. Did we all catch that?
Yep.
Okay, cool. If you didn't, think about it some more. Okay? This formula is particularly important. Okay? This is sort of one of the first tricks that you learn when taking antiderivatives. And there are many more tricks to come. Okay? Fun stuff to look forward to after the break. All right? But do remember this thing. Okay? This little trick. If you want to get the antiderivative and you have a quotient, see if you can figure out how to express the quotient as f prime over f for some f. Okay? That's trick number 1 that you're learning today. All right. By the way, negative ln of cos x is also ln of secant x. Okay? Just put the negative 1 up. Yeah. So if you see the formula looking like this, don't panic. Where is the formula valid? Everywhere except at certain places, asymptotes. Okay? Now, absolute value, yeah, it's better to do this. Okay, I agree. All right. It's not that the formula is incorrect. Usually you see ln of secant x, you know. But then again, secant could be negative, you know, in certain intervals it is. So it's better to put the absolute value. Now the formula is valid not just within certain intervals, but actually everywhere except at the points where we have an asymptote. Okay? So same case as over here. So anytime your answer involves a ln, you can stick an absolute value in there and make the answer more general. Okay? Cool. All right. Other special functions. If you know how to do tan x, you'll know how to do cotan x. Okay? This is sine. This is cos over sine, right? And cos over sine is sine prime over sine. So what is the antiderivative?
Ln off cosine.
Yeah. Okay? And again, check it. If you don't believe us, take the derivative. 1 over sine times sine prime is cos. Cos over sine, cot. Add the absolute value if you want to extend the range of the formula. Now, I'm going to tell you 2 other formulas which are important, okay, for secant x and cosecant x. But you're not going to need to know how to derive them. So I'll just tell you what the formula is. One of these is slightly easier than the other, but I really don't think you'll be expected to do this. Correct me if I'm wrong. How much work have you guys done with antiderivatives?
1 hour. That's it.
1 hour?
1 out, yeah.
Okay, cool. So yeah, you probably won't be expected to derive that. Especially this one is sort of a hard problem. Okay? But anyway, I'll give you the answers so that you know them. This one is ln secant x plus tangent x. Okay? And this one is ln cosecant x minus cotangent x. Okay? There's another way to express it. I think it's something like this. Yeah. But actually, confirm me. I'm not sure if it's exactly sine of x over 2. Maybe it's ln of cusc x over 2. Yeah, I think it's that. Cusc is cosecant. All right. Yeah, so you can check these formulas by differentiating. I just told you them because they're useful, okay? And you're going to need to know them next semester anyway. Okay, is there anything else which you need to know? E to the x. What's the antiderivative?
I wonder. E to the x from a plus c. Okay.
Oh yeah, that's right. Yeah, yeah. I forgot about the plus c, like entirely. Okay, yeah. Okay, yes. So, why do we put the plus c in there? We do want the most general antiderivative. So an antiderivative is not unique. We could add any constant we want. Differentiating gets rid of the constant. It kills the constant, and it turns into 0, right? So if you want to actually get the indefinite integral or the antiderivative, do remember to add the plus c. Don't be like me, okay? The antiderivative of e to the x is e to the x plus c, okay? By the way, a nice little exam problem, one sec, would be prove that if two functions have the same derivative, then they differ by a constant. Basically, prove the plus c property. Okay? So exam question, and I know this is a possible exam question because I've seen it on an exam. Okay? So possible exam question, prove that if f prime of x equals g prime of x for all x's, then f of x is equal to g of x plus c. I'm not going to do it. You're going to do it in preparation for the final exam. Okay? And if you can't succeed in solving this, the proof is in the book. Okay? So, possible exam question, prove that. This is the plus c property. Okay? I'll just put that in there. Plus c property of indefinite integrals, right? If we didn't know that this was the case, you know, basically what we're proving here is that the antiderivative is unique up to an added constant. If we didn't know this was the case, maybe we could have two completely different antiderivatives here in different form that just happen to work. We know that's not the case. There's one and only one plus any constant that's arbitrary. Okay? So when I say that this is also can be written like that, what I'm really saying is that ln of sine x over 2 is exactly the same for all x's as ln of cos x minus cot x plus possibly some constant. Okay? And you can confirm that again yourselves. All right. Yeah, so you need to know e to the x. I can tell you a couple more. You'll need to know, let's say, what happens when you have a general exponential like b to the x. Okay?
Like a to the x.
Yeah, a to the x. Okay? What's the antiderivative of a to the x?
A to the x is going to be ln a.
Very good, right? The trick is this. You write this as e to the x ln a. And then you take the antiderivative as you would with e to the x, and you divide by the ln for the same reason why you divide by the n plus 1 here. Okay? So the anti is going to be a to the x over ln a. Okay, cool. And of course, the formula in this case works for positive a's only. If you want to know why it doesn't work for negative a's, try graphing something like -2 to some power and see what you get. Okay? The base cannot be negative. Okay? Okay, so that's that. I can tell you a couple more. Here's one. Ln x. What's the antiderivative? You gotta be a good guesser. Yeah. So if you don't know how to do the antiderivative, just guess and hope it's right. Okay? Just keep generating new guesses and check. Okay? In this case, we can check 1 times ln x plus x times 1 over x minus 1. The 1 and the 1 cancel out. It works by checking. Next semester, you'll learn how to actually derive this. There's another technique called integration by parts. Okay? Did you guys do substitution?
Yes.
Yeah.
Oh, okay, cool. Before we get to that, actually, there are other formulas available, but you can get them just by looking at a table of derivatives. For example, what is the antiderivative of this? 1 over 1 plus x squared.
Oh, arctan.
Yeah, arctan. Okay? So, know your derivatives, and you'll know your basic antiderivatives. All right. Now, here's a question I have for you. What is the antiderivative of this? We're running out of room here, aren't we? What is the antiderivative of 1 over 1 plus, I won't put 1, I'm going to put 3. What is the antiderivative of 1 over 3 plus x squared?
Arctan x over 3.
Close. There are two ways to think about it. One way is to take the formula and mess around with it to make it look like this one. Okay? Another way is to use the substitution technique. I'll show you both. Here's the first one. I'm going to factor out the 3. Why? Because I want 1 there. I want to get this formula to look like that. So I'm taking out the 3, okay? And the formula is going to look like this. And now I don't want a division here. I want everything in one piece all squared, right? Because that's the form that this is in. So I'm going to write this as 1 over 3 times 1 over 1 plus x over root 3 all squared. Okay? And now after we get it into the right form, we make our initial guess. The guess is arctan x over root 3. We start with our initial guess, and then we modify things, possibly, if we need to account for the chain rule. So if we start with that and differentiate, we do indeed get this term, but then we also multiply that by 1 over root 3. We don't want it just multiplied by 1 over root 3. We want a 1 over 3 in there. So we gotta divide by another root 3. Okay? So the right answer will be this. And you can check it. Take the derivative. Okay? The derivative of this is going to be 1 over root 3, 1 over 1 plus x over root 3 squared times 1 over root 3 by the chain rule over here. Well, root 3 times root 3 is 3, and we get that. Okay? So that's one way. The other way is to do substitution. And to do substitution, you do this. You have 1 over 3 plus x squared dx, okay? Here's how substitution works. You're going to introduce a new variable. You're going to let u equal something involving x, okay? In this case, since I've done a lot of questions like this, I know what to put. What do I put? Something which produces a 3 in front over here. So then the whole 3 will factor out, and we're going to get exactly that for our arctan. Okay? So I'm going to let u be root 3x. And again, why do I do that? Because I want the 3 to appear here. Okay? If I do that, okay, this is what happens to the integral. We get 1 over 3 plus 3, wait a sec. Oops. We want x to be root 3u. There we go. So 3u squared. Okay, cool. And now we have dx over here. All right, so there's a bit of a problem because we have u in there and x in here. So if we set x equal to root 3u, what is dx? It's root 3 du, okay? Just take this formula and differentiate it as if x was just a function of u, okay? Differentiate it, dx is root 3 du. So we replace the dx with root 3 du. Cool. Now we can factor out the root 3 and the 3 from the bottom. This will be root 3 over 3 integral du over 1 plus u squared, which we know is arctan. Okay? Get rid of that. So we know that this thing here is going to be arctan u. Root 3 over 3, by the way, is just 1 over root 3. Right? That's how I know that. Yeah? Root 3 squared is 3. Arctan u. The last step in substitution is to replace the subbed-in variable with the original variable. Original variable was x. X is what? It's u over, u is what? It's x over root 3, if you divide through by root 3. So this is 1 over root 3, arctan x over root 3. Okay? And that's how you do a question with substitution. Okay? So, here's a challenge. All right, exam question. Okay? What is this? The indefinite integral of x over 1 plus 4x squared dx. Okay? I'm not going to do it. You're going to do it. Okay? So, if anyone wants to try this question, give it a go, and then I'll show the answer at the end of the seminar. Okay, in the meantime, are there any other specific antiderivative questions you want me to do? Are there any other questions from the rest of the course that you want me to do?